Following on from the previous video, we got to this stage here. We got to this stage here. So from here, you can always translate this to this. So we got to a stage where anything in this interval here, we know the power series is going to converge. We need to check when it's dead on -1, and we need to check when it's dead on +5. So let's have a look at the case when it equals dead on -1. So when x equals -1, this was our power series. So we would put this -1 into the x. So -1 minus 2, that will be -3, and then basically put this into here. That will then give you this, and then rewrite this as this. So now this here is the number 1. No, this here is the number -1. So this is your -1, and then now it really boils down to us trying to determine if this will converge or if this will diverge. Well, two methods of doing this. One is to use the alternating series test. So the alternating series test would be you trying to extract this un here. So you would be extracting this un here. So this is your un here. Make sure it's all positive. So all the UNs are positive, which will be from n is moving from 1 to infinity. So this is always positive. Make sure it's heading towards 0. As n heads towards infinity, this will head towards 0. So this is good. And then make sure that the next term is always less than or equal to the current term, meaning it's always it's non-increasing. Well, looking at this, it's always non-increasing. So all three conditions have been satisfied. Therefore, we can conclude that this will converge. And we've done this many times in the past, so you should already know this. But a better rather than using the alternating series test, you could use so we were here at the moment when x equals -1, it led us to this. So now it boils down to us trying to determine if this will converge or if this will diverge. You could just use the absolute convergence test. So take the absolute version, because the theorem saying that if you look at the absolute version, if the absolute version converges, then the original thing will also converge. Well, if you take the absolute of this, that's the same as absolute of this. So you can pretty much ignore this thing here. It's going to be the number 1, and then you can see that this is a p series where this is greater than well, this here will converge. We've seen this many times. It will converge. Therefore, this whole thing here will converge. So this is a better method than the alternating series test. So now for the case of when x equals 5. So when x equals 5, put it into here. So that would be 5 take away 2. That would be +3. So in the case of x equals 5, that would then give us this. So now group these two together. That will then give you this. So this here is just the number 1. So now you can see p series where p equals 2. So we know we recognize that this is going to converge. So a summary of what we've done so far. We wanted to find the domain for this function, meaning we want to find out values of x for which this power series will converge. We would then use a ratio test and compute this value here, an plus 1 over an. We would then compute this value here, n tends to infinity. Well, this value here turns out to be this. We want to know when this will be less than 1. Well, it will be less than 1 in the interval from -1 to it would be less than 1 in the interval from here to here. But then dead on -1, this value here will then be equals to 1. Well, the p series, when this, sorry, not the p series, the ratio test, when this equals 1 is inconclusive. So when it equals 1, we've just manually checked it that this will converge. Therefore, you can include the -1. when x equals 5, this value here will equal 1, which will be inconclusive. So we have to manually check this 5 here. Well, we manually checked it, and it turns out that it will converge. Therefore, you can include 5. So the domain for this function here is from -1 all the way to 5, and it's centered at 2. Okay, so that's your domain here. It's from -1, and it's from -1 to 5, inclusive of 5. Okay, so this is your domain here, from here to here. Okay.